So I want to start by thanking the organizers for this conference and all the speakers, because it's been really great so far. So thank you very much, and thank you for inviting me. And I'm going to start just by introducing the growth-unique ring of varieties. So we have this ring, which is defined to be the free abelian group on varieties over a field K, and this is the last time I'm going to write the base field there, because otherwise I'll just be writing it a lot. And we quotient it by the following relation. Whenever we have a closed subvariety, y of x, we're going to say that x is y plus the complement of y in x. And multiplication is just Cartesian product. So the goal of this ring is to sort of encode varieties up to cutting and pasting. So the idea is if you want to cut out a subvariety y of x, you can just do it, and then x becomes the sum of those two, and you can cut those up, and you can keep cutting, and then you can start gluing back together in a possibly different manner. So you can see that if two varieties, if you have a variety and you cut it up into pieces and you reassemble those pieces to make another variety, those two varieties will be equal in this ring. So on one hand, it encodes this nice combinatorial geometric property. On the other hand, just a warning, this is a really bad ring. First off, we don't know what it means if two varieties are equal in this ring. I've just told you a nice property that implies equality, but the reverse implication does not hold. And we do not have any characterization of what it means when two things are equal. We know they have the same dimension, but there's lots of varieties with the same dimension. We don't really know what it means. And this is sort of one of the open questions about this. But even just, okay, like even if we don't know what it means, it's a bad ring. It has 0 divisors. It's just any kind of geometric thing you try to put on it seems to not really work. For instance, you might think it should be filtered by dimension, but it's not. Like you can take the thing saying we're generated by varieties up to dimension n, and take that, and that should be a subring, but it's not. It has a map in there. So like just, it's really bad. But on the other hand, it keeps popping up in places, so we would like to know things about it. Well, there's sort of a law of nature that whenever you have something like that looks like this, like you have a group completion, you have things that you know how to add but don't know how to subtract, there is a K-theory spectrum associated with it, and the group will be pi 0. So I'm not going to tell you what K-theory is. I'm just going to tell you what kinds of things have K-theory and what the K-theory means, and then we're going to keep going. So the law is that whenever there's a group completion, there is a K-theory spectrum. And there's going to be a couple of minor/major lies in the following list. Please ignore them. So first off, if you have a symmetric monoidal category, this has a K-theory spectrum, and K0 is going to be the group completion of objects in fact, morphisms with whatever your symmetric monoidal structure is. The second example is whenever you have an abelian category, we have exact sequences. And then K0 is going to be the group completion of objects with the relation that whenever you have one of these, B is A plus C. And the last example is that whenever you have a model category, you have, we're going to have cofiber sequences. So we have cofibrations A into B, and we can take their cofiber, and then K0 is the group completion of objects, well again, mod isomorphism and mod isomorphism with A plus B mod A equaling B, and oh, sorry, I didn't mean isomorphism, I meant weak equivalence, obviously. So we have these kinds of relations, we have a bunch of things about how to construct K-theory. They exist, and you can look them up. Weibel's K-book is a great place to start if you want to see all of these in one place. if you notice, the category of varieties is not one of these. Like, it is symmetric monoidal under disjoint union, but we don't want the relation that we have to just be disjoint union. So the category of varieties actually is not one of these. However, for an abelian category, we can replace it with exact, where we just know that there are exact sequences. And it turns out that in an amazing weirdness, the category of varieties acts a lot like an exact category. And there's actually a very rigorous way that I could say that, and it's awesome. We can talk about it after the talk. But in fact, if you want to talk about this fact, you should talk to Jonathan Campbell, who first noticed it and is in the audience right there. So this is a very cool fact. So we can take its K-theory, and the K-theory will produce a K-theory spectrum where that is pi 0. Now, the cool thing is that this spectrum is actually, in some ways, better than this. It is a spectrum. It's an E-infinity ring spectrum, which you want if you have a commutative ring. But moreover, I mentioned like this doesn't have a filtration by dimension. The spectrum does, and we can compute its associated graded. So it's actually a better object than this ring. So studying the spectrum makes sense. And you can try to use it to try to compute things about this ring. But as usual with K-theory, you know, adding K-theory to something doesn't make computation easier. It only makes it harder. So if we want to try to compute things about this ring, maybe looking at the spectrum isn't the best way to do it. On the other hand, you know, I know the theme of this conference has really been computation, but I can't do computation. So I'm going to just try to figure out properties of this spectrum and leave the computation to people who are way better at it than I am. So instead, I'm going to say, OK, well, what can we figure out about this spectrum? For instance, is it an Eilenberg-MacLane spectrum? It could be that it actually contains no information other than this ring. So in fact, it's not. So fact. So this K-theory spectrum of varieties is not an Eilenberg-MacLane spectrum. And this is actually easy to prove. So, yeah, so here I need K to be finite. It's actually true even if it's not finite, but the following proof will only work if it is finite. And this is the proof I want to give. So we have a map from finite sets into varieties, which just includes them as the zero-dimensional varieties. We have a map back to finite sets, which for a variety x takes its k points. And you can see that this composition is the identity. And therefore, in fact, the K-theory of varieties has a sphere spectrum that splits off of it. So in fact, we see that, finite sets is an example in this family. And so we can apply K-theory here. And then the K-theory of finite sets is actually the sphere spectrum. So we have a copy of the sphere spectrum that splits off of the K-theory of varieties. So we have this reduced K-theory of varieties, and we have the sphere spectrum. But in particular, since we have a sphere spectrum, we know that pi 1 is non-trivial. Yay! So pi 1 here is non-trivial, and we know it's not an Eilenberg-MacLane spectrum. OK, great. But like, this is the boring part of varieties, right? It's the part of varieties that doesn't know that they're varieties. It's like only working with finite CW complexes, but we're only going to talk about the zero-dimensional ones. It's not topology. So this is the interesting part. So the next question is this reduced K-theory an Eilenberg-MacLane spectrum? And this is the goal of this talk, to answer that question. So spoilers, math has an exoskeleton style of writing, so we always spoil everything so that you're not sitting on the edges of your seat. The answer is no, which is good. If it was, it would be kind of depressing. So let's figure out how to do this. How did we do this? Well, what we did was we actually found a spectrum that we could map to where we could find an element in pi 1 of the spectrum that was hit by this map. And we did it by actually splitting off a nice spectrum, but we don't have to do that. We can just try to find some other spectrum that we map to and an element in pi 1 that we can hit, and that will be good enough. Actually, mapping out of this thing is kind of hard, so I'm going to be mapping out of this thing too, and then I'm going to check that on this part it goes to 0, so that's all good. So what we're going to do is we're going to construct derived motivic measures. And I just want to give you these buzzwords because you might see them in the future, and I want you to know that what this means is this is a map, K of V, to some spectrum X. That's all it means. If you have a motivic measure, that's a group homomorphism out of the growth and decaying of varieties to some abelian group. If it's multiplicative, that means it's a ring map or an E-infinity map, but we're not going to be worrying about those today. So that's all this is under all of the buzzwords. So let's see. To find these measures, what we want to do is take classical measures and lift them. This is, in fact, what we did right here. So we're going to lift classical measures. So I'm going to give you a couple of examples of classical motivic measures, just so that we know what these things kind of look like. So the first one is point counting, which is exactly what we did over here, just taking a variety to its k points. OK, this is the only place in this entire talk where I'm going to assume that k is c. For everywhere else, it's finite. So when I don't write it, it's finite. So we can take the following thing. We can take a variety x, and we can map it to the sum over all I of -1 to the I. Take the cohomology with compact supports of the complex points of x with rational coefficients. And this is going to live in K-theory of the rationals. So each of these is a finite dimensional Q vector space. So we have, this is a formal sum of them. Since the generators here are finite dimensional Q vector spaces, this is a well-defined element in here. And I wanted to draw your attention here. This is really important. It's cohomology with compact supports. And that's simultaneously really, really important and really, really bad. So it's important because if we want this to be a homomorphism out of that, it has to satisfy the additivity relation. It has to be the case that when you have a y including into x, the variant you get for x is equal to the one you get for y, and for x, the complement of y and x. And the thing is that the complement of y and x is open most of the time. And so if you just take ordinary cohomology, you don't get a nice relationship between the closed set and the open complement and the whole thing. But in cohomology with compact supports, you do. You have this long exact sequence relating them. And so this Euler characteristic is actually an invariant that satisfies that additivity relation. So that's really, really important. On the other hand, it's really, really bad because cohomology with compact support isn't functorial. It's covariant with respect to open inclusions and contravariant with respect to closed inclusions. So it's not a functor. So I can't just draw a picture like this and say apply K-theory and everything is happy, because it's not. It's not a functor. You can't do that. So on one hand, yay, we can do this. And look, this looks like an Euler characteristic, and it lands in a K0, which means that we might be able to do it with K-theory. And on the other hand, it's not a functor. Problem. It's OK. We'll solve it. So now going back to our usual finite case, we can do the exact same thing. This is for complex varieties, but there's a version of this, which is L-adic cohomology, which works for varieties over finite fields. And in fact, I'm not going to say the whole point of L-adic cohomology is that this works, but it kind of is. So you could take x mapping to the sum, -1 to the I, of cohomology with compact supports. And this lives in K0 of QL. So you can do this. It works for exactly the same reason. The whole point of L-adic cohomology is that it satisfies all the same properties as ordinary cohomology, so this works by construction.
Are you here also taking the sequence of x?
No, x is a finite. is finite. So this is L-adic homology. So it looks the same, but it actually isn't. It's a much more complicated construction, which is why I'm completely glossing over it and just saying it behaves like that. OK, that's great. And I want to do one more example that's not going to look like the other ones. I want to point out there's also K0. That's K0. There's a possibility we might be able to make this work. So the last example is the local zeta function. So x is going to map to z of xt. And this is a power series. So you take the number of x points. So I'm going to just write k as fq for e. So this is fq to the n, t to the n over n. And this actually lives inside the ring of power series with coefficients in z under multiplication. From this formula, it's not obvious the coefficients will be in z, but trust me, they'll be in z. So we look at this, and we say, well, that's not K-theory. You can tell it's not K-theory because K-theory only remembers finite things. As soon as you put infinite things into K-theory, you get Eilenberg swindles, and bad things happen, and you only get 0. And so K-theory can only ever work with finite things, for some definition of finite depending on your context. But power series have an infinite amount of information in them. So this isn't really a K-theory thing. Actually, kind of is, but anyway. And the thing is, it shouldn't be really living in here, because we know from big number theory theorems that zeta functions are rational. And so even though it looks like it contains an infinite amount of information, it actually only contains a finite amount of information, as it should if it's K-theory. And so this already feels a little bit strange. This looks like it's sort of a bigger generalization of this. Here we only remember the x points over fq. Here we're remembering the x points of all extensions of fq. So somehow it feels like, OK, you can extend this using that. And you can, but again, you lose this finiteness information. And we don't want to do that. We want to remember that zeta functions are rational. So if we're going to construct derived zeta functions, we're going to lift this to a map of K-theory, we want to remember that it is rational. We want to remember the finiteness. So luckily for us, there's other mathematicians out there who did really cool work. And in particular, we know that K0 of the endomorphisms, in this case of z, although later I'll be working with q, there's a map here with a nice kernel. And in fact, this is going to live in here. So I'm going to describe this map. So first off, what is end of R? This is a category where the objects are pairs PF, where P is a finitely generated projective R module, and F is an endomorphism. And the morphisms are things that commute with these endomorphisms. So you go PF to QG by H, and you just need whichever one it is. You have F and H and G, and going around one of these and then going across the same as going across and going around the other one. And I'll write them in the wrong order if I try not to do it as a diagram, so you can figure it out. The point is that all morphisms commute with the specified endomorphisms. And then to get a power series out of an endomorphism, we're just going to map PF to the characteristic polynomial of F. And so that might be positive, it might be negative, it might be inverted because we're under multiplication, but it'll actually end up in there. So we have this map, and in fact, the kernel of the map is just those endomorphisms where F is 0, those pairs where F is 0. So somehow, there is a kernel, but we really don't care about it. And the fact that zeta is rational ends up being here. This is, in fact, hits all rational functions in here, so zeta will land in here. And now we're back to looking at a K group. So we're going to try to land in something that looks like that. Okay. So our goal is going to be to lift this to a map of spectra, somehow compute it on some element of K1 of varieties, and note that it is non-zero. And then that will mean that we have elements in K1 which are non-zero, which will make us happy. Okay, so how do we do this? Well, first I want to make a couple more comments about these two examples. There's actually more structure on the cohomology of a variety over C than just the cohomology. There's this whole mixed Hodge structure here. And in fact, if you carry along the mixed Hodge structure, the Long-Zach sequence in cohomology with compact supports respects that. And so, in fact, you end up in K0 of mixed Hodge structures. So we can carry along more information. So what we're going to do is we're going to look at this example, figure out how to get this example out of it, and go through here. And this is so that we will use cohomology with compact supports as our functor, although it's not a functor. Okay, so how are those two related? Well, we have the Lefschetz fixed point theorem. First off, notice that the fixed points, so x of fq to the n, is the fixed points of Frobenius to the n acting on x. So remember, Frobenius takes every, say, if you're embedded in a nice if you're embedded in fq to the L, it takes every coordinate to the qth. And so this will take each coordinate to the q to the nth, and that's going to be the elements that are in exactly the ones that are in here. So now we have this as the fixed points. And we don't actually need the set of fixed points. We just need the size of the set of fixed points. And that's going to be, by the Lefschetz fixed point theorem, that's going to be exactly this sum. Frobenius acting on HI. This is part of the construction of L-adic cohomology, that this works. So we have the Lefschetz fixed point theorem, which tells us how to do this. And notice that now we are back to much closer to looking like the third example over there. So now we can say, OK, really, that last example is just a repackaging of the previous one if we remember more information. And we can remember more information. If you actually remember the action of Frobenius, this is Frobenius to the n, obviously. If you remember the action of Frobenius, that will, on everything, it'll remember the action of Frobenius to the n on everything. So what we really want to do is we want to think of Frobenius acting on the cohomology with compact supports, which is already looking much more like K0 of endomorphisms. But in fact, it's actually slightly easier, instead of just remembering Frobenius, to remember the entire absolute Galois group of FQ acting. So we're going to remember that. So we're going to, so we want to land in the continuous representations of the Galois group of FQ on QL vector spaces. So this is where we want. And right now, if I was going to lie to you, I would say something like theorem. Oh, and I forgot to say at the very beginning, sorry, this is joint work with Jonathan Campbell and Jesse Wolfson. So theorem, Campbell, Wolfson, and me. There exists a functor from varieties into there, such that on K0 it's blah, 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 blah. And I'm not going to finish it because this is not actually a theorem. This is a blatant, dirty lie, because as I mentioned, cohomology with compact supports is not a functor. So this is what we want, and we know it's not true. So we're going to need to fudge around with stuff until we can get something that is true. Okay, so firstly, what is the problem with making cohomology with compact supports a functor? When we're working with topological spaces, if you look at all possible compactifications, so one way of doing cohomology with compact supports is to do the cohomology of the compactification relative to the extra points you added. And in the category of compactifications of a given topological space, we have a nice, consistent one, which is the one-point compactification. And in fact, in that category, it's going to be the terminal object. And so that's a nice functorial way of doing it. We take a space, we take its one-point compactification, things work, we take its cohomology, everything is happy, and Robert's your mother's brother. But with varieties, that doesn't work, because varieties don't have a one-point compactification. So again, if you look at the category of compactifications of a given variety, that's going to be co-filtered, so it's going to be contractible, but it is not going to have a terminal object, so we don't have a way of mapping into it in a functorial way. So what we're going to have to do is we're going to have to choose to make all possible choices and then forget them. So we define this other helper category, varieties with a choice of compactifications, and we can forget the compactification to get down to varieties. And the objects in here are obviously pairs of variety and a compactification, and the morphisms are just commutative squares that commute with this. And mumble, 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 things go wrong, mumble, weak equivalence is mumble. There's an issue here that you now need to end up adding weak equivalences to your K-theory. You can no longer work with it as though it's an exact category. But that is totally fixable, and Jonathan fixed it. And so now we have this functor. And the proposition is that K of U is an equivalence. Fortunately, it's a weak equivalence rather than, say, a homotopy equivalence, but whatever, it's an equivalence. So now we have variety with compactification, so now we can functorially take cohomology with compact supports. And we're all happy, except we don't land in there. So if you want to take cohomology with compact supports so that K-theory works correctly, you actually need to land in chain complexes because we don't have a notion of a negative vector space. The role that is played by a negative vector space is generally played by vector spaces in odd dimensions in a chain complex. So we can't, we have an honest alternating sum there. Some of those vector spaces ought to be negative. So we have to go to chain complexes instead of the standard. But we have this. We, in fact, don't only need bounded chain complexes, or homologically bounded mumble-mumble. So things work reasonably well there also. But these two are not the same. Luckily, there's a theorem that I'm going to, it's Julian Waldhausen, but I don't know how to pronounce his name, so I'm just going to mumble it. Which is that the K-theory of a ring, including into the K-theory of bounded chain complexes on that ring, is an equivalence. And here, the ring sits, our modules sit in degree 0, and this is an equivalence. And if you're following along, you notice that this goes the wrong way. So we now have, I did not use the board ideally, but anyway, we now have So we started off wanting a map here, but we actually produced this zigzag. But luckily, all the reverse maps are weak equivalences, and we can do nice things and kind of invert them up to homotopy, so we can pretend we have a map at least on the k-theories. So once you apply k-theory here, this is an equivalence, this is an equivalence, and so we can pretend that we have a map here. And that is the map that we are going to call zeta. And this is the theorem, this diagram. Like, that's actually true, so it's a theorem. Okay, so now we have this map, and we want to say, okay, how are we going to pick out an element in K1? What is K1? We've been talking about K0 a whole bunch, and I told you what K0 ought to be, but I haven't told you anything about K1. So what is K1? So just a couple of examples. So K1 of finite sets, as I mentioned earlier, is Z mod 2, because it's the sphere spectrum. But you can also think about it in terms of what K1 should be. So if we're thinking of finite sets as a symmetric monoidal category, as a symmetric monoidal groupoid, really, because you want finite sets up to isomorphism, what you're doing is the one simplices that you get when you construct this are given by permutations. Those are the automorphisms of finite sets. And so the elements in K1 are going to be representable by automorphisms. And then you put them all together, you group complete, and this messes up K1. But what it really does is it abelianizes things. It says if you do sort of one of these automorphisms and then you do another one, you end up you want it to be abelian. So what does this mean? Well, the abelianization of a symmetric group is Z mod 2, and it's given by the sign. And the sign of a permutation is really size invariant if you think about it. So it's saying if you have a permutation of length n and then you add a bunch more elements on which you're not doing anything, it doesn't change the sign. And so this is sort of the biggest size invariant, I'm blanking on the word. The thing that doesn't notice size invariant of a permutation. Yes, thank you. And so literally takes a permutation to the sign. So if you wanted to find a non-zero element in K1 here, you would just take up any odd permutation of a set. And if you think about it, that's actually exactly how we found this element in K1 of varieties before. Like, you can take 2 points and the permutation that permutes them, and that's going to map to something non-zero in the K-theory of varieties, and that non-zero element is going to be exactly going to map that back down to this sign. Like, this is really how we did it. So now let's think about K1 of more complicated things. So K1 of a field is the multiplicative subgroup of the field. And it's doing exactly the same thing. It's saying, OK, we have a finitely generated projective F module, meaning a vector space. We're taking an automorphism, that's a matrix, and we want an invariant of this morphism that doesn't notice when you add trivial stuff at the bottom. And that's the determinant. So this is given by determinant. And this is, in fact, why sometimes you will say that the determinant on the matrices of a commutative ring lives in K1. Like, this is sort of what is being alluded to in fields. It's really given by the determinant, and sort of the place where the determinant, it's the place where the determinant correctly lives. And so when you do K1 of R, well, I can't give you a nice formula for it because it depends on the ring, but the determinant of a matrix lives in there. So we have this. And in fact, in general, this is the same thing. Even once you add in weak equivalences and like in a model category or something more complicated, you an element in K1 is given by the zigzag of weak equivalences that starts and ends. This is meant to be a zigzag, not a composition. That starts and ends at the same object. That's, morally speaking, what K1 is thinking about. There's some nice presentations, actually, for K1 of exact categories. In varieties, an element of K1 is given by you take a variety, you decompose it into pieces, you reassemble the same variety out of those same pieces. That is what an element of K1 is. So those are really complicated. There's a lot of them. And remember, when we write it this way, these aren't going to necessarily commute past each other. So when we're taking K1, it takes these and then it abelionizes and does all sorts of nasty things to it, makes it stable. And so we do not know of a presentation for K1 of varieties. We don't know presentations for K1 of many categories. We know generators. We know some relations, but it is, in fact, in general, unknown whether those are all relations. There's a hypothesis that it is, but that's unknown. So, okay. So these are hard to find. But that's okay. We don't actually care about knowing what element of K1 we're doing. We just want its image under this map to be non-zero. All we care about is that it's non-zero. And we don't actually need a general element of K1. We just need to pick a nice one. So let's take X to be smooth and projective, which is the variety version of compact. So in fact, X comma X will live up here. And we're going to take an automorphism of X. So phi is an automorphism. So that's a perfectly good zigzag. It's a zigzag containing one element, which is actually an isomorphism, but that's all to the good, makes life easier. So we get a map. So in general, we have a map from aught X to K1 of C whenever X is an object of C and C has K theory. In general, this will be much, much larger than this. So usually this homomorphism is very high, has a very large kernel, and is in fact often zero and makes it harder to detect things. But this is true in general. So now we know that we can do aught X. So that was sort of an aside. We can do aught X going to K1 of varieties. And now I'm just going to map directly into here because I have a natural compactification to choose, so I might as well just not worry about that first reverse arrow at all. We know it's an equivalence on K theory, so if one K1 is non-zero, the other one will be too. And then we're going to map to the K theory of these continuous representations. And now we go, that thing is huge. And we don't actually want to work with it. But luckily, we don't need to, because, you know, as I mentioned before, we actually only care about the action of Frobenius. And we kept this because it was easier to construct this functor. But now that we're actually trying to work with it, why not go back to the thing we actually need? So we can forget this down and be in K of aught of QL. And it's actually going to be important in a second that we're in aught and not end. We have a map from aught to end just by forgetting that we have to have an automorphism rather than an endomorphism. So Frobenius is actually an automorphism, so we're remembering it here. And sorry, and these are K1s. So these groups are actually this and K1 of endomorphisms. There's been work on them. It's known vaguely what they are and how to work with them. And the goal of this project was actually to show that its image in here is non-empty by directly computing where it will map to in here. But we kind of had some problems with that in that we can't figure out how to compute in here. Like, we know there are generators and relations, but we don't know where this maps to in here. So in terms of those generators and relations. And so That's a bit awkward, so we had to go further. And in fact, for a very long time, we were working in K1 of n and just got completely stuck because we had these generators and relations. We had a completely different presentation for where we map. We couldn't figure out in terms of those generators and relations, and we were just going back and forth. So if anyone has experience with working with K1 of n, we would love to be able to just directly show it's non-zero in there. However, this is actually better for what we're about to do. So what is K1 of ought? Well, ought is going to be exactly the same here, except I'm going to replace endomorphism with automorphism. So what is a morphism in here? Well, it's just an automorphism in here is an automorphism that commutes with the fixed automorphism, right? So I said that elements of K1, that automorphisms represent elements of K1, and that's exactly sort of what we're doing when we're tracing through here. And what ends up happening is you end up with a vector space with two different commuting automorphisms acting on it. And what is represented by pairs of commuting automorphisms? Well, it's K2. So we have a map from here to K2 of a field. And I didn't talk about K2 at all because K2 is hard and complicated. But we do have this map, and this map has a nice, it's called a description, it's called a star product. And it also has a Hilbert symbol. So we can map from this to the roots of unity in QL. This is the Hilbert symbol. And the only thing that actually matters here is in the case when L is 2, so in this case P, which is the characteristic of our field, is not equal, whatever, I can do it here, is not equal to 2. So in this case, what it does is an element of K2 is represented by two elements. So this is a pair AB with both of these in QL cross. And this map will map to 1 if A or B is a square, and -1 otherwise. So what we want is we want to find an automorphism that maps to -1 here. That's represented by two numbers, neither of which is a square. Now, I'm just going to check for you. So I'm not going to do this calculation because it's number theory and I don't know number theory. So I'm going to tell you what the automorphism is, and then I will tell you that if you know number theory, you can do this calculation and you get the correct answer. But first, let's check it on the automorphism where you just have 2 points and commute and swap them. Because the whole point was to find a different element than that. So I want to check that that maps to 1 so that I don't need, so that as long as I can find anything that doesn't map to 1, I'm good. So we're letting x be 2 points. And our automorphism is going to be swapping. And so here, well, down here, what is the QL automorphism that we get? Well, our cohomology with compact supports is just going to be QL squared. So we get QL squared, and the automorphism, the pair of automorphism that acts on it, there's going to be swap from here, and there's going to be the trivial from the Frobenius, because Frobenius doesn't do anything on zero-dimensional things. And so what happens in this particular case, not always, but in this particular case, to map down to here is you just take the pair of determinants of these. And in particular, the determinant of the trivial map is 1, which is a square, and so we go to 1. So swapping 2 points gives you something trivial. On the other hand, if we take 2 copies of P1, and again, we just swap them. We don't even need to do anything complicated. We get -1. And this is where you need to go talk to a number theorist, because I don't actually, like, in terms of how you get the number here, like, I can tell you a bunch of buzzwords, but I don't actually know what they mean fully. So my number theory collaborator says it's -1. So we get this, and we're all happy. Yay! We got an element in K1 that's not the Z mod 2 from swapping 2 points, which means that the reduced K theory also isn't an Eilenberg-MacLane spectrum. And technically, we accomplished the goal of the talk. Woohoo! But in talks like this, like, I was lying. I didn't really care about computing the element in K1. I really just wanted to construct the zeta function. Like, that was the goal of this project, to construct the zeta function. And then at the end of the project, like with any kind of project, you say, OK, well, what can we use this for? What can we prove with this? And then you have to sit and think of like a reasonable justification you can tell people. So that is the reasonable justification, which I think is kind of cool. But on the other hand, I think it would be even cooler if we had a general purpose algorithm for constructing motivic measures. And in particular, if like we could lift the mixed Hodge structure motivic measure for complex things, that would be awesome. We can't do that yet, because it turns out that the stuff you need for mixed Hodge structure is more complicated than just a compactification. So that's sort of next steps in this and things that we would really like. And as a smaller thing that we would really like is like if we could actually figure out what the image was in here without having to go down to Z mod 2, I'm pretty darn sure that if we could compute in here, we could find a lot more interesting elements and find interesting relationships in here and like learn a lot more about automorphisms of varieties and K1 of varieties than we do just by mapping down to Z mod 2 this way. So I'm certain that there's something more rich and interesting going on there than this particular projection shows. And if anybody knows how to compute with these, I would be absolutely thrilled to talk to you. So thank you. Once you take the K theory and choose inverses up to homotopy for these two equivalences, you have a map of spectra.
Okay. I just have a comment. So the K theory of automorphisms and the K theory of endomorphisms and a lot of these other types of K theories of these types of categories, I think they were studied by Grayson. There are papers by Grayson on these things. And so there is a kind of analog of the Bass-Heller-Swan theorem in this setting, and so maybe that would be.
Well, those are the generators and relations we were working with. It's just actually figuring out in his presentation where you actually mapped what you hit when you do this map. Like we couldn't figure that out. It's a very nice presentation, but it's not really designed to map into directly from varieties. No. Yeah, no is the short answer and the long answer.
Can I just ask you what model for K theory, I think you down, what model for K theory do you prefer to use in all of this?
For this particular application, we're using, well, for this, there's two models of the K theory varieties. There's one that uses assemblers and a Waldhausen structure, and there's one that uses Jonathan's SW structure, and Jonathan's SW structure is beautifully suited for this. So we're using SW categories, which are not a standard thing, which is one of the other reasons I glossed this over, because it doesn't actually fit into any of the standard things. But the thing about SW categories is that a huge number of the theorems for exact categories work there. And so that's why I said, oh, it works like an exact category, and you can think about it that way.